Hi, we're going to continue with statistical thermodynamics, and um, this last topic, C, is focused on how you can determine or calculate the thermodynamic properties from knowing the partition function. So I'm going to break it into two sessions just because it's a bit dense, and that might help you digest it in smaller bits. Okay. The origin of thermodynamic properties. So we're going to understand how you can extract internal energy, heat capacity, enthalpy, and last and most importantly, the Gibbs free energy, so we can understand how you can actually calculate an equilibrium constant from partition functions. So this first section has the key idea that the molecular partition function contains all the information needed to calculate the thermodynamic properties of independent particles. And you could also calculate the properties of particles that are interacting, but that's just more complex, so we're not going to do that in this class. So remember that the partition function is equal to this sum. It's the sum of the exponential form for each energy in the state or in the system. And essentially it tells you the population, because as the energies get bigger, this term gets smaller, and so less high energy states are populated. So how can you get the internal energy just from knowing Q? So the first thing we want to think is that, and this is just exactly in the text, I've just written it larger. So the total energy of a system would be equal to the population, or the number of molecules in that state, times the energy of the state for each and every state that's populated. So that would be equal to summing over I, n sub I, E sub I. So the energy of each state times the number of molecules in each state, and you sum that up and you'd have the whole energy of the system. So we want to think about equilibrium. So if you have a system of water sitting on the table, it's going to be in equilibrium, and we want to know what the internal energy is for that particular state of the system. So if it's in equilibrium, we can use Boltzmann's distribution, and Boltzmann's distribution says the population of any state, so the number of molecules in state I divided by the whole sample, the whole number of molecules in your sample, so the fraction of the molecules in state I, is equal to e to the minus epsilon I divided by kt divided by the partition function. And this is just what we were introduced to in the first section of this focus 12. So we can rearrange that Boltzmann's distribution and solve for Ni. So essentially just take number of molecules over to the right-hand side. Then we can go back to our expression up here, and every place you see Ni, which is only once, you can put in N, e to the minus epsilon I over kt over Q. And then this is still here because that's the, that's the EI. So Ni times EI. N and Q don't have indexes, so they're just numbers multiplied by each term. So you can just distribute that through, or you can pull it out and multiply the sum by N over Q. So we can take N over Q out of the sum, and we end up with the sum over EI, e to the minus EI over KT. And this is really epsilon. I'm calling it E just because E sounds more like energy. But the symbol that they use is actually epsilon. So how does this relate to Q? So we have Q here, but we want the expression completely in terms of Q. So you'll notice if you take the derivative with respect of T of e to the minus EI over KT, you get the exponential function times the derivative of the exponent. And so you get e to the minus epsilon I over KT, and then the derivative of that exponent with respect to T. When you take that derivative, bring this back in a second, you're really taking the derivative of a constant times t to the minus 1 if you're taking it with respect to t. And so that's the constant times the derivative of t to the minus 1. And so that would be minus 1 pulled out front times t to the minus 2. So that minus 1 out front cancels this, and you get t to the minus 2. So epsilon I over k, t to the minus 2. And so if you just take that t to the minus 2 into the denominator, you get the energy of the state divided by k t squared. And so if we look at that, then the derivative that we just took here, if you multiply it by k t squared, you will cancel this, and you'll end up with just this, which is exactly what our sum was. So that means taking the derivative and multiplying by kt squared will give you this, which is what I'm trying to solve for. So if we put that back in, so go, let's see, go here, and we have, you can't see that. Go here, and we have n over q, whoops, n over q sum over all these. And so we have n over q sum over, and now the sum is going to be over kt squared. Yeah, kt squared times the derivative of this guy, because we know when you simplify that, that equals the epsilon I e to the minus epsilon I over kt. So we're at this point. Now we can just simplify that. We can look at this derivative. So a sum of derivatives is also equal to the derivative of the sum. So we can pull the d dt out front. And then the d dt is of this sum, and this sum just happens to be q. So if you pull the derivative out front of the summation, because a sum of derivatives is equal to the derivative of the sum, we end up and we see that the internal energy is number of molecules, Boltzmann's constant, t squared over q, and then the derivative of q with respect to t. So all you need to know is q, and you can get that internal energy. That internal energy is relative to some 0-point energy. And so when you talk about the internal energy of a system, it's going to be what the internal energy is at 0 plus this epsilon for all of the populated states. So the epsilon that we are talking about is based on Boltzmann's distribution. So we're talking about the energy as a result of what the population of states are. So how many are in the N0, how many are in the N1, N2, etc. So that's the internal energy. And so if we look at the self-test, here, sorry about that. So if we look at using this in self-test, C.1, it asks us to calculate the molar internal energy of a gas of diatomic molecules, taking into account contributions from translation and rotation. So we want to look at how we use this equation that we just derived. So what do we put in for Q? So it says we have diatomic gas molecules, and they have a contribution from rotation and translation. So the equation we're going to use is this one. So the internal energy is what it would be at absolute 0 plus this contribution from the populated states. And the total Q is QR times QT. So it's the rotational partition function times the translational. The translational partition function, we learned about that in the last topic. It's this set of terms. So it's the volume, the temperature, Boltzmann's constant, mass, Planck's constant. The rotational partition function was KT over the symmetry number, Planck's constant, the rotational constant. So if we write out the entire Q, which is just a product of those two, I've just multiplied these all out. What we end up with, the important thing to notice is that it's a function of t to the 5 halves. So we had t to the 3 halves and t, and so that's t to the 5 halves. And then all this other stuff is just a bunch of constants. So Q equals a constant times t to the 5 halves. So when you take the derivative of Q with respect to t, you get 5 halves, the constant times t to the 3 halves. And then if you look at putting in this stuff, so that's dq dt, but we need to multiply that by na k t squared over q, which put in right here. And then this is the derivative. So these are the constants and this is the derivative. And now what you notice is if I want to separate out q, what I need to do is take one of these t's out, and so I have a bunch of I have NaK over Q and one t left, and I'll take this t out, and when I do that, I get 5 halves, that same constant, and another t out here. And when I do that, what you notice is constant times t to the 5 halves is Q. So I have, when I look at this, Na times K equals R. So Na times K is R. So I have RTQ, and then I have 5 halves, and then I have constant times Q. And so the Q's cancel, Q top and bottom, and I have RT 5 halves. And so internal energy is equal to the internal energy at 0 degrees plus the population of states contribution essentially, so plus 5 halves RT. So using this equation isn't a big deal because we know the functional forms that we're going to use for each of those Qs. So it's a fairly easy equation to deal with. Then the next thermodynamic property we can determine is the heat capacity. So the next section talks about the heat capacity, and all you really need to remember is what the definition is. So the definition of heat capacity is how does internal energy change with temperature holding volume constant. Then, for example, for the above problem, if I wanted to know the heat capacity for this system, I would take the derivative of this with respect to t, and the derivative of a constant is 0. The derivative of this with respect to t is 5 halves r. So the heat capacity for that system we did in the self-test would be 5 halves r. So once you get the internal energy, it'll be fairly easy to take that derivative. So go ahead and stop and do self-test C.2. See if you can get that to work out to be the same as the answer that they get. Shouldn't be too hard. Same concept of putting in your Q, and then for the heat capacity, taking the derivative once you get the internal energy. For our next thermodynamic function, the entropy doesn't go through a derivation of this. If you take 366, we'll derive this in detail. He just lets you know that if you start out with the definition of entropy, S equals K ln of W, and we look at equilibrium where W is the maximum, the entropy will end up being U minus U0. So the internal energy relative to what it is at T equals 0 divided by T plus NK ln of Q. And that's for a solid where the particles are held in space and you can distinguish them from each other. You know this particle's right here. Versus for a gas, an indistinguishable particle where the gas can move around, that decreases the entropy some because not all the states are different if you can't tell the particles apart. So it's the same functional form except you subtract from it n times k times ln of n minus 1. So it doesn't show you where that comes from, but we will use that equation. And so I did self-test 12C.3, and his answer he gets assuming that the particles are distinguishable, whereas I use this one because ethane at 25 degrees should be a gas. And so I'm thinking that my answer is right, unless I come up with some other idea after I sleep on this. I think 7.49 is wrong times R, because ethene would not be a solid. So let's just look at doing that problem. So it says the rotational partition function of an ethene molecule is 661 at 25 degrees C. What's the rotational contribution to its molar entropy? And so the molar contribution to its internal energy is just that RT factor from what we learned about back in the equal partition of energy. So that will be RT because we're just talking about the rotational contribution. So entropy will be RT over T plus NAK ln of the partition function minus NAK ln of the partition function. Ooh. That's where I went wrong. So this would be ln of Avogadro's number. So I'll have to go get my calculator. So I feel like that's going to make the molar contribution negative, which cannot be true. So let's look at how they did it. They did it assuming it was a solid. And so you would just have R plus R times 6.49 and you get 7.49. I have to relook at this. I don't know why I put that there. It should have been N if we're looking at the molar contribution. So if we're looking at the molar contribution, then Avogadro's number times K equals R. So this would be R, this would be R, and this would be ln of Avogadro's number minus 1, which still seems to me will make the number negative, which makes no sense. You can't have a molar contribution to an entropy that's negative. So I will check that, and when we start my next lecture, which will be on Gibbs free energy, I'll confirm what the heck is going on with that problem. What they did was just these first two terms, assuming it's a solid, and I don't think that's right. So I'll check what my answer will give with my calculator.